So what we'll do today's class is look at the 5G NR protocol stack, and there are lots of protocol stacks and lots of layers to deal with, unlike internet where we talk about TCP IP stack. So here there are lots of stacks. So I will try to give only the overview of the main layers and how they are kind of play role when you are using cellular networks, in this case 5G. So let's see how much I can cover today, and I will continue the coverage of these layers in the following class on Friday. I was showing you this slide earlier as well, which is kind of showing the functionality split between base station and the 5G core. And can somebody tell me what is the interface that we use for the connection between these two entities?
NGU.
NGU. So it is the user plane. And also, can you tell me, Madhuri, what is the kind of stack that we are using on NGU?
GTPU and the UDP TCP IP stack.
You are absolutely right. So I want somebody else to answer this part. So what is this interface? So Harinder, can you comment?
Sir, maybe it's needs cells.
No, I'm asking what is the interface that is used for connecting base stations with AMF?
So I can't recall it.
Okay, and Devang, can you answer?
So I was not, I have not gone through yet. So,
And who wants to answer? Satvik, can you answer it?
Actually, I can't recall it.
You can't recall it, even though it was covered in the previous class, is it?
Yes.
Okay, so who wants to answer?
NGC.
So the hint is also there in the slide. It is the NG control plane. And what is the stack that we use it here?
SCTP UDP.
SCTP and?
UDP IP.
No. Again, you are confusing.
IP.
Yes, because SCTP is an equivalent of TCP or UDP at the transport layer. So this is what we have seen in the previous class. And I was also telling that even if you take two base stations, let's assume that you have another base station here. Let's call it as another NGRAN. So there we are using XNC and XNU, which also uses similarly the GTPU tunnel for the user plane traffic and uses SCTP and IP for the control plane traffic. So these are the things that I'm having again here in this slide. So just look at these illustrations. So what you see in this slide is how a base station is kind of providing the connectivity between user, which you see on the left hand side, with the core network. And where you can see the control plane part. So this is where I was talking about using SCTP. So the main point you should be noting down here is the base station here is only a pass-through device. That means all the messages that user wants to exchange with the core network in the control plane are just forwarded by the base station. For the reason why I'm calling it as a pass-through device, the base station. And we call these messages, especially these are related to the authentication, registration, and mobility related. These are called non-access stratum messages. And then you see here, I'm showing you the NGU interface, which is the user plane. That's where we will be using GTP and IP. And interestingly, you can see it here. There are two links are the barriers that are established here, or you can also call it as GTPU tunnels. So the reason why we use the tunnel here is by having this tunnel, user doesn't have to change their IP address. Unlike mobile IP, where we talk about when user moving from one network to other network, you should be assigned a new IP address. Then we have this care of address and home address and other things. But that is not required in the case of cellular networks. All the way from GPRS, that is 2.5G, 3GP has defined something called GTP tunnels, using which your mobile device can retain the IP address no matter which base station it is connected. The reason how it can still retain the IP address is base station doesn't speak IP. Unlike routers or switches in internet. As you connect with another router or switch, you'll be assigned one IP address in that particular subnet. That is not the case here because base station only talks about layer 1 and layer 2, not even layer 3. Of course, even though we have the GTP tunnel on which we will be using UDP and IP, that is separate. But on the user plane between the handset and the base station, it is only speaking layer 1 and layer 2. So that's the reason why we use these GTP tunnels to be able to roam the users across the base stations without changing their IP addresses. We'll discuss on this part again later when we talk about handovers. So in summary, this is what we have seen in the previous class, where on the control plane we are using SCTP over IP, and on user plane we are using GTP with UDP and IP, where it is possible to have more than one such tunnel where you can connect this user equipment with more than one UPF, not just a single UPF, it can connect to more than one UPF. And a similar thing can be also talked about XN. That's what I was just mentioning about. This is the interface that is there between these two base stations, where we'll be using XNC and XNU, using which two base stations talk with each other. The reason why they have to talk with each other is one is for the handovers, other one is for radio resource management. That means addressing the interference problem for cellular users. And in the case of dual connectivity, also you need this interface to be able to split the barriers or having some kind of signaling between the base stations to be able to send the data to users at high rate or with high reliability. So in all these cases, this interface uses. It is also exactly similar to NG interface in terms of using GTP and SCTP for carrying the signaling traffic and user plane traffic. So let's come to the today's class where I will talk about the 5G protocol stacks. I'm talking about stacks, not just a single stack here. Let's look at on the left hand side. This is the user plane stack. And what you see here are the physical layer, MAC layer, radio link control layer, packet data convergence protocol, and other one is SDAP layer that stands for service data adaptation protocol. So you see these are the layers that are terminating at the G node B or at the base station on the right hand side. And the user equipment side also we have these layers. You have to assume that above this layer is where your IP packets of TCP IP come into picture. So similar, that means when your user equipment is generating IP packets using TCP IP stack, this TCP IP stack using these layers below. So these 4 layers that you see it here, they corresponding to layer 2. And this is anyway the layer 1. And this is layer 3, and this is your layer 4. And the above we have your application, different application that you wanted to have. So this is the user plane stack. And unlike internet, here in cellular networks, we have not only the user plane stack, we also have the control plane stack. where we'll be using different protocol stack, different protocols, not completely different. To some extent, there's a difference between the kind of protocols that you use for carrying signaling data and the user traffic. The way you have seen, we are using GTP tunnels and SCTP. Same thing can also be talked about when the base station and user equipment talking with each other using interface called U interface, where we use this interface for both control messages and also for user traffic. Let's look at the control plane stack. The main difference that you can see it here is that these are the two entities at the user equipment side that comes into the picture when you're talking about the control plane stack, which are missing in the data plane. And HDAP that you see in the data plane or the user plane is not there in the control plane. That is clear for you, right? And if you look at on the base station side, only RRC is the one that is terminating at the base station, whereas the NAS, that is a non-access stratum layer, is terminating in AMF. But on the user side, yes, we have both NAS layer and RRC layer in the control plane, but one of them is terminating at RRC, other one is terminating at AMF. So let me show you before going further, what is the protocol stack that we have in the 4G and how it is similar with the stack that I'm showing it here. This is the 4G stack. We also call it as LT stack. So look at the similarity between this stack and the previous stack. So if you look at very carefully on the user equipment side, what you can say? On the user equipment side, what you notice?
It's kind of that both user plane and control plane stack services are there, if compared.
Okay. Yeah, Harinder, that is not true completely. Maybe I should show you this. I think maybe I'll just hold on. Yeah, so okay, maybe this is the right picture to show you in the context of 4G. Okay, this is the 4G stack, okay, not the 5G.
So there's a direct connection between the user equipment and the core network in the NAS earlier.
Direct connection.
Yeah, I mean it's there's no protocol as such to in eNode V, the base station.
No, I didn't get. Are you talking about NAS or are you talking about something else?
NAS, sir.
Okay, just hold on. Okay, other than that, what do you see it here? So as you see, this is also another way people show the protocol stack by depicting both the user plane and control plane side by side. So let's look at the user side. What this basically means is that these 4 layers that you see it here, these are common for both user plane and control plane. Okay, whereas when it comes to the user plane, which is on the left hand side, we don't have RRC and NAS. We simply take IP packets and you send it over the PDCP layer. Okay, that is the meaning of putting the user plane stack and control plane stack next to each other. And in the control plane, if you look at the stack that you see it here at the user side is exactly what I was showing you in the case of 5G. We have the same RRC and NAS, where RRC is terminating at the base station and NAS is terminating at core network. Whereas in the case of 5G, I was showing that it is terminating at AMF. Whereas in the case of 4G, it is terminating at MME, which stands for Mobility Management Entity. And here I'm not showing you the stack. There's also another stack. Maybe I will show you after a few minutes. See, here I'm talking about how these two are talking with each other in user plane and also in the control plane, where you see a different set of protocols, even though there is a lot of commonality between them, but there's a slight variation between them. Let me go back and show you. Okay, so can you see the stack it here? Look at the control plane where RRC is terminating and where NAS is terminating. Do you see any difference between 4G and 5G, where we are terminating RRC and NAS? No response from anyone. Do you see any response, any difference here or not? The way we are terminating RRC and NAS.
Sir, RRC is getting terminated at the base station, but NAS is getting terminated at AMF instead of MME. I mean, I think that's
Yes,
the only
yes.
difference.
That is the only difference. That way you can assume that it is exactly the same in the control plane when you take the 4G stack and 5G stack at the high level, at least. Of course, when you go to the inner details, yes, there are some optimization, some tuning that has been done. But when you look at the user plane, what I was showing you is SDAP is the new layer that has been introduced to offer quality of service in 5G, which is a kind of not there in the 4G networks, in the 4G stack. Okay. Let me come back and show you what is 4G stack and what all these layers do, because at high level, the functionality that I'm showing it to you here is also applicable for 5G networks. That way you can see it is a kind of evolution of 4G stack in 5G systems as well. All of you know about the physical layer doing both modulation and coding. And the MAC layer is the one that does the scheduling, including something called hybrid ARQ. So all of you know about the role of ARQ, which is meant for providing the reliable delivery using protocols like stop and wait or sliding window protocol. So we use something called hybrid ARQ, where we try to send packets and don't discard even the partially correct packets, and we try to combine these partially correct packets to reconstruct the original message. That's not what we typically do. Typically what you do is whenever your CRC check or FCS fails, you discard the packet and give negative feedback to the sender so that sender will retransmit entire thing again. But the beauty of this is when the channel is inherently lossy, each time when you are getting some part of the packet correctly, the idea is by getting same packet transmitted multiple times, you can able to get some bits correctly in each and every retransmission so that you can able to reconstruct the original message after multiple retransmission of the same message. That's what the hybrid ARQ says. We do something called segmentation and concatenation. I will show you how they will be helping in splitting large packet into smaller packets and combining smaller packet into larger packets. Again, we have ARQ even at the RLC layer. Look at it very carefully. I'm showing you ARQ not only at the MAC layer, I'm also showing you ARQ at the RLC layer. That way we have a double reliability at these two layers. Then we have PDCP, which does header compression, and also it does encryption and integrity protection. Then we have the RRC, which is kind of the brain of the base station in terms of getting the user connection accepted and also getting the user authenticated, and also when the user is moving, handovering the user to other base stations. All that is taken care by the RRC. RRC is the only layer that is exclusively for the control plane that you can see here. Then we have the NAS, which are the messages which are kind of between the user equipment and the core network, where eNodeB does only the pass-through in terms of user registration, authentication, charging, and other kind of services. So these are kind of explained bit more detailed here. I don't want to go again, maybe because I'll show you that these things in the case of 5G. But at the high level, the PDCP layer, that is Packet Data Convergence Protocol, does the header compression, because for voice over IP, the payloads are very, very small. But when you're taking IPv4, IPv6 headers, the headers are kind of jumbo headers and the overhead is significantly higher. So we can optionally do the header compression at the PDCP layer to kind of reduce the header size of the IPv4 and IPv6. We also can do the integrity protection And also we can do the encryption of the data using AES and other kind of symmetric protocols. So we have one such entity for a radio bearer. I will explain what I mean by radio bearer in the following slides. Then we have RLC layer, which I was showing you does segmentation and concatenation of the compressed PDUs. It also does ARQ so that we can have reliable data delivery. And it also does in-sequence delivery of the packets to the higher layer. So these are the kind of two complementary services that you can get here. Then we have the MAC, which does the multiplexing of the traffic of the different users and send it over the air using the time and frequency resources. Then you have the physical layer, which does all these things. Okay, so let me, so this is the one I was showing you about RRC layer. It is the only one that is there in the control plane stack in 4G, and for that matter, even in the 5G also it is the same thing. It carries something called system information. That means each base station advertises what are the frequencies that it is supporting and what is the LO transmit powers and modulation schemes, what is the cell ID, what is the operator's network name and other things. Lots of broadcast information are carried inside these RRC messages. And also it is taking care of the connection control in terms of establishing the connection, releasing the connection and modifying the connection. And when you're getting incoming call or incoming messages, it does something called paging, where it sends certain control information to over all the base stations where the user is potentially located, so that your handset start ringing or starts receiving the messages and SMSs. It also takes care of the handovers and mobility, and especially when you're in a location where the link quality is very bad, it also try to reconnect to the another base station or for the same base station. That is called recovery from the radio link failure. And you can also use it for mobility across multiple radio access technologies like 4G, 5G, or 4G and Wi-Fi. And we can also do something called the measurement, configuration, and reporting. So the cellular networks depend on lots of reporting from the handset so that the base station can appropriately serve the users in terms of getting the channel quality and other information from the users, including the buffer status and what is the current battery status of your handset. All that information can be conveyed to the base station so that it can take the decisions. And okay, so this I was showing you earlier as well. So I hope this part is clear. This is the 4G stack, not the 5G stack. Okay. Okay, here you can see how the base station is connecting with serving gateway, and serving gateway is in turn connecting with packet gateway over different interfaces. So this is the U interface between user equipment and the base station. Then we have something called S1U interface. Then we have S5 or S8 between serving gateway and packet gateway. So again, try to look at what I'm showing it here. The IP packets are sent down this protocol stack, and the packets will be delivered over the radio network to the base station. So what the base station does, it repeals the layer 1 header, then it repeals the MAC header, then it removes the RLC header, then it removes the PDCP header. After you remove the PDCP header, so what is the thing that you have with you?
Normal IP packet.
Yes, now we have the normal IP packet that your application has generated. When it's IP packet, I'm talking about IP packet which is carrying either TCP or UDP traffic of different applications. Now look at what we are doing here. You take this IP packet and you add this GTP header. So let's call it as my IP packet. Then I'm adding GTP header to that. That's what is done by this layer. Then look at what you are doing it here. Then you are adding UDP header. Then you are adding IP header. So then you are pushing down this protocol stack. Yes, then it reaches the serving gateway which removes layer 1 and layer 2 headers. Then we have the UDP IP headers that also get repealed. Then the GTP header also will be removed. So again, you end up having IP packet here. The same IP packet that was there, again you got it here. So you repeat the same process again of again creating another GTP tunnel between serving gateway and packet gateway. Finally, the same IP packet lands at the packet gateway, that is nothing but your router. So anyway, router does the forwarding of the IP packets, and accordingly it will reach the corresponding destination system or destination node. Is that clear what I'm trying to say here? How, again, same thing is done even in 5G networks as well. There is no difference except that some of the protocols have been added or modified for 5G networks. Otherwise, at high level, I can say that this is how the 5G packets get routed between the core network and the users through base stations. Any comments or any queries on this part?
Sir, we are aware that there are some advantages of using different interfaces for sending the control and user information, right? So why don't we have a different interface from UE to eNode B? Like why just we have one interface?
No,
for both
again, Madhuri, even though I'm saying that we have U interface, we will be using this interface to send both control plane and user plane traffic.
Yes, sir. But then control traffic should have more priority than the user traffic, right? So,
No, look at here. Are you able to see my slide here?
yes, sir.
So we are using the U interface, okay? And if it is control packets, they will be originating here, okay, in general, okay? And if it is user traffic, yeah, so these are the user plane. We have something called bearers. So I will be talking about that later. So we have different kind of bearers. Bearers are nothing but connections, logical connections. We have data radio bearers. Another one is called signaling radio bearers. So whenever you connect a handset to the base station, by default, your handset will be provided with one data bearer and one signaling bearer to exchange all the user traffic and all the signaling traffic respectively. It is also possible to establish even multiple data bearers. We wanted to prioritize different kind of IP flows that you are getting. So this traffic, that data bearers and signaling bearers traffic, is carried inside this interface. But I think your question is about how can we guarantee more priority to the signaling traffic over the data traffic, or for that matter, when you have multiple data traffic sessions that are going, how to differentiate between them. All of them are done when you are actually establishing the data bearers by the MAC scheduler. So MAC scheduler is the one which is aware of what is important and what should be sent urgently and what can be delayed or kind of deferred. All that is taken care by the MAC as part of the scheduling. So is that clear, Marti? No, not Marti, Madhuri.
Yes, sir. But then when there is communication between two or more network functions, we have different interface like XNU and XNC. So even there also we have MAC schedulers working, right? So
Oh, no. Wait. There's no MAC scheduler there. Okay. So why do you think there's a MAC scheduler here? So look at here. There's no MAC scheduler here.
oh, okay. Yes, sir.
There's
Okay.
no MAC here.
Okay.
Because 3GPP doesn't define how the base station should be connected with serving gateway, how serving gateway should be connected with packet gateway. Only we need this logical interface with certain QoS guarantees. It doesn't define what should be your L1 and L2.
Okay, sir.
Only here on the radio network side, we completely define the steps and we say what each and every layer should do, where the MAC takes the center stage in terms of guaranteeing the QoS and also giving high priority to the signaling traffic over the other traffic.
Okay, sir. Thank you.
Okay, so this is another slide. Maybe I can skip it, but if you wanted to really look at this, is how the flow of the IP packets happens between the base station and the user equipment. Look at how you do the things. So you are getting IP packets here of the different users. In this example is, here I'm showing the downlink, okay? So this is for the downlink. So look at what is happening. The base station is getting the IP packets. Then we have something called PDCP entities. You can treat like PDCP instances or PDCP threads, where you create one PDCP instance for each radio bearer that you see it here. That's why you can see there are lots of nested things that you see. Header compression. It is not that I have only one function that is doing header compression. For each radio bearer, we can have separate header compression thread that is running at the base station, where it will take the packets of one user and start doing the compression, if at all the compression is enabled. Then you do the encryption by agreeing upon what kind of the encryption protocol that you wanted to use. Very often we will be using AES. Then we have a segmentation and ARQ. I was showing you earlier as well. Then at the MAC layer, we does the multiplexing, and also we do something called hybrid ARQ. The only thing you should be noting here is, at the PDCP layer, I have multiple instances. And even at RLC layer also, I have multiple instances. But the MAC is the one, it is a single instance, which is common for all different RLC instances. And it is kind of does the multiplexing of these logical channels. So I will talk about in the following class what these different channels are really meaning. But at the high level, you can assume that by saying the channel, we kind of treating the traffic that belongs to that particular channel differently compared to other channels. For example, we can say I have control channel and I have data channel or the traffic channel. So where you can try to give differentiation in the way you treat their traffic at the MAC scheduler level. And then we have the physical layer. And if you look at on the right hand side or the left hand side, we have the MAC scheduler. So this MAC scheduler is the one which is interacting with all the three layers, not only the MAC layer, RLC layer, it is also interacting with the physical layer, using which is a kind of getting some inputs from these layers. And also it is kind of dictating what modulation scheme you should be using, what antenna should be used for serving user, and what should be the transmit power. All that scheduling decisions are kind of conveyed to these three layers, so that we do the segmentation and you decide what kind of ARQ protocol that you wanted to use and how do you want to multiplex. So all these are kind of thing taken care by the scheduler. And also other important thing is the scheduler is running only at the base station, where the scheduler does the scheduling not only for downlink, it also does it for uplink, where it is does something called scheduling grant, where it is informing the user equipment that, okay, you can transmit to me at so and so time. So in advance, the base station decides who should be talking at what time with it. And that information is carried as control information and send it down when the base station is sending the traffic in the downlink. So yeah, that way the scheduler is very complex and it does most of the things. And when you talk about 5G, where you are talking about different use cases, network slicing and other thing, scheduler really becomes even more complex, and it takes really the center stage in achieving these kind of guarantees and providing network slicing and other QoS guarantees for different slices and use cases. And you see here how the data is flowing in 4G networks. So this is an example where you see there are three bearers. You can assume that bearers are nothing but three logical connections. Where you can see that there are two bearers, okay, not three. So these two are the IP packet that belongs to same bearers, same bearer. And here I have IP packet that belongs to second bearer. So this is bearer 1 and this is the bearer 2. Look at what PDCP layer is doing. It is taking the SDU, that is so the one that you get it here, PDCP SDU is nothing but IP packet. So what PDCP layer is doing, it is adding its header, and after adding the header, you call it as PDCP protocol data unit. And it gives that to the RLC layer. We call it as RLC SDU. RLC SDU is nothing but
PDCP packet.
PDCP PDU. Okay. Then what? And also you should be noting here, if you observe very carefully, RLC layer is doing something very interesting. Look at here what it is doing. It is taking this packet, and is creating one combined RLC packet. So this is what I meant by concatenation. So this is the concatenation, and also you can see the segmentation here happening here. Where you are taken one RLC SDU, that is the PDCP header with the IP here. So you have taken this and you are splitting that into two parts. So that RLC does both the concatenation and segmentation. Then look at what MAC layer is doing. So it has taken two RLC PDUs. That means it has taken this one and this one together and is created. That means the MAC layer is also doing concatenation. And is creating something called the MAC packets, which we also call it as something called a transport block. So what physical layer does is, physical layer adds CRC. So interestingly, in cellular networks in 4G and also in 5G, this is an example of 4G, we have the CRC added at the physical layer. So in general, we talk about CRC32 and other thing added at the MAC layer in the case of Wi-Fi and also in Ethernet. But here you can see the CRC is added at the physical layer. And then we have the transport block together with the CRC ready at the physical layer. So this is the one sent over the TDMA / TDD or TDMA / FDD, depending on which mode of the LTE you choose for operating at the base station. So this is shown again in the slide. If you look at one more time. So you can see these are my IP packets. The PDCP is adding its header. So these are the PDCP PDUs. And what RLC layer is doing here is it has taken these two PDUs or these two packets from PDCP layer and it is doing the concatenation. And also you can see a small segmentation also happening here, especially this N1 packet is split into two parts. One is kept here and rest of the thing is kept here. Then the MAC layer is the one that is taking these RLC PDUs and creating the MAC PDUs. If needed, it also does the padding. After that, we have something called a transport block, which is ready to send it over the air, where the physical layer adds CRC header to this. And you map this over the TDMA frame. So that's what I was mentioning in the previous slide. In LTE, we have TDMA frame of length 10 millisecond, which is further divided into 10 subframes, where each subframe is divided into two slots of each 0.5 milliseconds. Okay, in other words, 500 microseconds. Each of these is 500 microseconds. What you are doing is, we are taking this 1 millisecond. This is 1 millisecond in time domain. So I'm not talking about the frequency domain. So frequency domain, it's all depends on the channel bandwidth. Channel bandwidth could be, let's say, 10 megahertz. Then we have so many number of resources that are available. I will show you all this for 5G networks in the following class or so. But at the high level, you can assume that we take the IP packets to the layer 2, where you start adding PDCP header, RLC header, and the MAC header by doing concatenation or segmentation to create something called transport block, to which the physical layer adds the CRC header. And take basically all these things, what I'm showing it here, these are all in binary format, zeros and ones. So still we are talking at the bit level. So we are not talking at the symbol level. Only at the physical layer, all the channel coding and modulation, all ADC conversion, all those things happen at the physical layer. Still, you're doing all this processing on the bit stream. That's why we call all this as the baseband processing, where you take this and you map into this 1 millisecond. Where in the time domain, we have something called 14 symbols in time domain. In the frequency domain, depending on the amount of channel bandwidth, you'll have more and more resource blocks. So yeah, in summary, this is what we do in LTE in terms of scheduling the traffic and multiplexing them to create something called transport blocks. So let me come back to the discussion on 5G, where I will show something at high level and show you in the context of the protocol stack how these things really make sense. Let me show you how we establish something called a PDU session. Okay, PDU session is nothing but a logical session that is established between the user equipment and the UPF. Okay, so the idea here is, let's have a pipe, a logical pipe. So this is what I'm calling it as a PDU session. In LTE, that is called something called EPC bearer. In 4G, it is called as EPC bearer. And here in 5G, we are calling it as a PDU session. So let's look at what is happening. Anyway, what you see is at a high level anyway. First, the user equipment, after successfully registering with the network and successfully getting authenticated, it is sending a request that is called PDU session establishment request. So this is what I was mentioning earlier about the NAS message. So this is a message where the base station doesn't do anything. It simply passes the message that is received from the user equipment directly to the core network. In this case, this message is being relayed to the control plane entity, that is the AMF, Access and Mobility Management Function. After it's seeing the request from the user equipment, look at what AMF is doing. It is asking the base station, why don't you go and start establishing a PDU session in the radio link between the base station and the user equipment. That is the step 2, that is PDU session resource setup request, where the G node B and user equipment have to kind of reserve the resources. When you say reserve the resources, we are talking about the channel resources or the radio resources. So that way it is kind of instructed the G node B to start reserving the resources for this new PDU session. Then look at what G node B is doing. It is invoking its control plane entity, that is RRC layer, to do something called RRC reconfiguration. So even though the name says reconfiguration, we also use it for configuration as well. So now it is kind of sending request to the user equipment. Why don't we both create one data bearer? This is called data radio bearer. Yeah, so the request is being sent along with the information that is coming from AMF to the G node B. That is the called RRC reconfiguration request that is going to the user equipment. So then what user equipment has to do is, it has to create this new bearer. So you may be wondering what it really means by creating this bearer. So I was mentioning that for each bearer, there is one PDCP instance that has to be running. There has to be one RLC instance that has to be running. That means it has to create threads. One thread at the PDCP layer and another thread at RLC layer, and it has to initialize the thread with whatever the setup related configuration, depending on the kind of PDU session that you create. So that is what it means by establishing the data radio bearer at the user equipment. After it is established at the user equipment side, user equipment is kind of acknowledging, stating that yes, it is successfully able to establish these instances at PDCP layer and RLC layer, and it is ready, including something at the MAC layer if needed, and it is ready to have this new PDU session. That is the acknowledgement. After the base station receives acknowledgement, it in turn acknowledges the AMF, stating that, okay, I have done what you asked me to do in terms of setting up the resources on the radio link between myself and the user equipment. So then look at what is happening after step 6. In the step 7, we have the UP stands for user plane. Okay. There are so many acronyms, don't worry. So here it stands for user plane. QFI stands for QoS flow identifier. So let's see what is happening here. Then in the step 7, the UPF is establishing a QoS flow with the base station. So we have something called a QoS flow. And similarly, we have a QoS flow between and Gnode B and user equipment. But again, all these are at the logical level. So what you are seeing here is user is making a request to establish a PDU session with the core network. Core network in turn asking the base station to do IRC configuration to establish a new data bearer. After this bearer has been established, now we have something called a new PDU session, where this PDU session can carry one or more QoS flows, where for each of these QoS flows, we can have something called QoS flow identifier. We have 66-bit field is available, using which we can differentiate different QoS flows. Let's example, you want to have YouTube running with a certain QoS flow identifier, voice over IP running with certain QoS flow identifier, your file download or email going over with a different QoS flow identifier. All that can be configured by something called your UPF and instruct the base station to do the mapping between these QoS flows to data bearers. That I will show you in the following slide. So what I was just describing with the call flow diagram in the previous slide is again explained in bit more detail in this slide. But yeah, the last point, it kind of says that the QoS marking over the U is optional, while the marking over the NU is always present. So what it says that this is must and this is optional. When the UPF and Gnode B are talking with each other, along with sending IP packets from UPF to, let's say, Gnode B, you also carry the QoS flow identifier. Typically, we use something called N3 interface between these three. This interface has some external extra fields. There you put the QoS flow identifier. Whereas here in the wireless link, the providing the QoS flow identifier when you're sending the data is optional. That's what it means. It is possible to enable it, but you can also disable it. Then let's look at one by one the various layers that are there in the protocol stack. So if you recall, at the top we have SDAP layer, then we have the PDCP layer, RLC layer, MAC layer, and physical layer at both the base station and also at the user equipment side. So let's look at what SDAP layer or SDAP layer is doing here. What you see here is the SDAP sublayer, and also I'm showing you PDCP sublayer so that you can see how they are kind of interconnected with each other. So look at what we have between PDCP and SDAP. We have something called radio bearers. The PDCP layer provides its services to HDAP layer in terms of radio bearers. So we have both signaling radio bearers and also we have data radio bearers. So depending on whether you want to carry control traffic or the user traffic. So these are the things. And we have at HDAP layer, you see there are two instances of HDAP that are running. You can assume like these are the two threads that are running. So depending on the number of PDU sessions, if I call it as 2, if I call it as 1, for each PDU session, you need to have one HDAP entity that is running. So this is my PDU session 1. So this is my PDU session 2. Where you can see a PDU session is nothing but a collection of one or more QoS flows, where all the QoS flows of a given PDU session are handled by one HDAP entity, where the HDAP entity simply does the addition of the HDAP header and pushes the packet the way you see it here to the PDCP layer. So we call them as HDAP PDUs, which are nothing but PDCP SDUs. So both are the same. Now look at what PDCP layer is doing. The PDCP layer is creating one PDCP entity per radio bearer. For each bearer, there is a separate entity. Okay. And one important point to note down is one or more QoS flows can also map down to one radio bearer. It's not that the mapping between the QoS flows and data bearer is one-to-one. You can have many-to-one, where you can take multiple QoS flows and you can map them to one data bearer. So this is again shown with another animation. So look at, so this could be user equipment talking with the base station, or this could be the base station talking with the user equipment, or this could be user equipment 1 talking with user equipment 2. So this is something called side link communication in 5G. So side link communication is important in the context of vehicular to vehicular communication. When you have these, we have 5G NR V2X is one flavor of the 5G NR to support vehicular applications like autonomous navigation, collision avoidance, location services, and other things using some band called ITS band, which is a licensed band. There, the vehicles can directly talk with each other, exchange their coordinates, their current speed, and trip-related information, or whatever it is as possible. For that, we have the side link channel that is defined. So there, again, we have two user equipment talking with each other without going through the base station. So it is like a called device-to-device communication as well, where the devices in the V2 are the vehicles flying on the roads, or it could be the drones flying in the air and talking with each other to do certain kind of activities that they're expected to do. So all that cases also being considered as part of the 5G. So look at what is happening here when the user equipment wants to talk with the base station. What you see is we have something called QoS flows. We have one or more QoS flows at the transmitting side. They are given to the HDAP layer. This is your HDAP layer, or you can call HDAP entity. So what it is doing, it is mapping the QoS flows to the data bearers. And there are two variants. There is one case where the HDAP layer is adding its header. The second case is it is not adding any header and directly sending the packet down. That means it is more like a kind of a pass-through. This is important when you are connecting the 5G base stations with EPC or the 4G core, where the HDAP layer itself is not defined. Or there could be some other use cases where you don't need HDAP entity at all. These are the cases. At the receiver side, you do exactly the opposite. So let me talk a bit more about what the HDAP layer is doing. If you look at the 4G stack, this is the only difference in the user plane between the 4G stack and 5G stack. The reason why we have this SDAP layer is to provide something called flow-based QoS in 5G. Even though we have QoS defined in 4G networks, it is not at the granularity at which we have defined QoS in 5G, where you have something called flow-level QoS in 5G, where we do this kind of mapping of the QoS flows to the data bearers. So that's what the SDAP layer does. It takes the QoS flows and maps them to the data bearers. Like, let me show you again with this animation. If you recall this call flow, we have a PDU session established between the user equipment and the UPF. We have a PDU session established. Basically, we are establishing a pipe. That is the one. This is the PDU session between UV and the UPF. Where, look at this animation or the illustration, you can see that this PDU session is composed of 3 QoS flows. Each down arrow that I am showing here can be assumed as one QoS flow. Also, it is important to note down that a QoS flow, a given QoS flow, one flow, one or more IP sessions. So try to understand what I'm trying to say. When the IP packets are coming from internet to the UPF, what UPF does is it creates something called QoS flows, where it can try to assign one IP session to one QoS flow, or it can take multiple IP sessions belonging to one user and treat together all of them as one QoS flow. So in this case, what I'm showing is this particular PDU session that is established between user equipment and the UPF is composed of 3 QoS flows, where each of them can be having one or more IP sessions between the user equipment and the UPF. Is that part clear to all of you? If not, I will explain you one more time. Is that clear what I'm saying? What is the mapping between IP sessions to the QoS flows, and how all of them are fitting inside PDU session? Is that clear?
Yes, sir.
Okay, so nobody else is asking, so I'm assuming all of you understood. First, we have the IP packets coming, which all of them are belonging to one PDU session, where the PDU session, which is created at the UPF for a given user equipment, is marking the IP packets into different QoS flows. In this example, this particular PDU session is having 3 QoS flows. Okay, let's look at what is done at the SDAP layer. So this is being done at the base station side. So look at what the base station is doing. The base station is also having the SDAP entity, where I was mentioning in the previous slide that we have one SDAP entity or one SDAP thread running for each PDU session. Look at the mapping that is done by SDAP layer between the QoS flows and the data radio bearers. As you see, we have taken 3 QoS flows and we have mapped them into 2 data bearers, where 2 of the flows have been treated together as part of the data bearer 1, and the third flow is kept as part of the data bearer 2 and is sent down to the PDCP layer, where for each data bearer we have one instance of PDCP layer that is running. That's why there are 2 data bearers, and you see there are 2 PDCP entities that are running, which take the packet that belonging to these 2 data bearers, and they do the compression, encryption, and other thing, and push down to the RLC layer. where RLC layer adds its header and send it to the MAC layer, where the MAC layer takes these multiple such RLC packets, where it multiplexes them and send it to the physical layer, where the physical layer sends all of them over the physical channels or the radio channels using the RF front end that it is having. So that is the flow that I am showing it to you here. And let's look at what I mean by marking of the QoS flow identifier. The HDAP layer does the mapping of the, or not the mapping, the marking of the QoS flow identifier both in the downlink and uplink. That means when the packets are coming, we add the QoS flow identifier. So if you recall, I was showing you again here. You look at here. Can you see the QoS flow identifier? So what it basically means is that when the UPF is sending the IP packets down, along with the IP packets, it also is including the QoS flow identifier in the extension field of the N3 interface. That's what is happening. So this is mandatory. So then we can also optionally send the QoS flow identifier when you are sending the IP packets over the radio interface to the user equipment. That is also possible. So that's what you can see it here. So it is doing the marking in both the downlink and uplink. So in the downlink, it is done by the base station. In the uplink, it is done by your user equipment itself. We also have something called reflective QoS flow to DRB mapping for the uplink HDAP data PDUs. What it basically means is that let's take a simple example where I have the user equipment and the G-Node B, where it is getting QoS flow. Let's assume that this QoS flow is a TCP flow. What it basically means is that we have to also send the acknowledgements in uplink, TCP-ACKs. In that case, we also need to have QoS flow defined in uplink. So far, we have certain QoS flow that is established in the downlink between the base station to the user equipment. Now the user equipment has to figure it out what QoS flow that it has to use to send its TCP-ACKs in the uplink to the G-Node B and in turn to the UPF. So what the reflective QoS basically means is that treat QFI in uplink is equal to QFI in downlink. That means you observe what is the QoS flow identifier of the downlink TCP packets, and you assume that you can use the same QoS flow identifier when you wanted to send the packets in the uplink. That is called reflective QoS. Basically, it is a kind of simplifying the thing, because if something is important in downlink, even the replies that is coming in the uplink are also equally important. So with that kind of intuition, they have defined this kind of reflective QoS, but it is also possible that you can explicitly use this RRC reconfiguration messages to have different kind of QoS flow with the different throughput, loss rate guarantees defined when you are sending TCP-ACKs also in uplink. Both are possible and both are defined in 3GPP specs when you're talking about QoS flows in the uplink and downlink. But the reflective QoS is the one that is kind of simplifies and reduces the signaling overhead, because you treat uplink QoS as that of downlink QoS. So let me talk about the QoS model that is there in 5G networks. As I was mentioning, it is defined at the granularity of the QoS flows. The QoS flows is the smallest granularity at which you can guarantee the QoS in 5G, where we have different kind of flows that are defined in 5G. Some of them are already there in 4G, and some of them are defined newly for 5G. So look at the first one. GBR stands for guaranteed bitrate QoS flows. As the name says, we are talking about giving certain bitrate guarantees. Like let's say if your application demands 2 Mbps as a constant data rate, then you can create a QoS flow which always ensures that you get 2 Mbps traffic, or sorry, 2 Mbps data rate between UPF and your user equipment. That is called guaranteed bitrate. This is important for guaranteed services. Then we have non-GBR QoS flows, which don't guarantee any kind of data rates. So this is for your best effort traffic, like your checking your emails and downloading files and other things. You can configure them as non-GBR QoS flows. And in the 5G, for supporting the mission critical applications, they have defined a new variety of the QoS flows. They're called delay critical GBR QoS flows. As the name says, these are meant for supporting URLLC use cases. Then I was just describing about the reflective QoS, where you treat the reverse traffic to be having the same QoS that of the oncoming traffic or incoming traffic, so that you can reduce the signaling overhead and start using the same QoS in treating the packets at the scheduling time. Then there are two steps I was also talking about in the previous slide. When you're talking about the mapping of the IP packets into the data bearers, in the step one, what you do is you take the IP flows or the IP sessions and you map to the QoS flows. So this mapping of the IP flows to the QoS flows are, okay, I think maybe word flow may be confusing. Mapping of the IP sessions to the QoS flows is done at the UPF. We call them as non-access stratum related mapping. So level 1 mapping is done by UPF, where it takes the IP flows and add the QoS flow identifier for each of the IP packet. So then we treat those IP flows or IP sessions part of that particular QoS flow. So then these QoS flows are sent it to the Gnode B. Then what Gnode B does, it maps the QoS flows to the data bearers. This mapping can be one-to-one or it could be many-to-one. But it cannot be one-to-many, okay? So that is not acceptable. So, so that is kind of shown again in this particular animation. Look at what is happening here. You are getting the IP packets. So this particular thing on the circle or the tying around these packets kind of says that these two belongs to one IP session. This is belonging to separate IP session, and these two. Basically, I have 3 IP sessions for a given user. Look at what the base station is doing, and not the base station. Before even the base station, we are doing the things at the UPF level, because it is the UPF which kind of defines the QoS flows and asks the base station does the mapping from QoS flows to the data bearers. Actually, the control of the QoS model is there in the core network, not at the base station. Base station has to simply obey the QoS model that is defined and has to provide the radio resources appropriately, so that you can provide guarantees that you expect for the different QoS flows. We have something called SDF. They're called service data flow templates. Using these templates, what you do is you take these IP sessions, that are the packets of the IP sessions, and you group them together into different QoS flows. In this example, you can see that these 3 IP sessions are mapped to 3 different QoS flows. That means there is a kind of 1:1 mapping, even though you can also map 3 IP sessions into one QoS flows, but in this case, you see only 1:1 mapping. So all the 3 QoS flows that you see are part of one PDU session that is established. For a given PDU session at the coordinate, at the access network or at the radio access network, in this case, it is the Gnode B, we use the SDAP layer. So we'll be using the SDAP layer to map these QoS flows into the data bearers. So this example is showing that these 2 QoS flows are mapped to one data bearer, and the purple QoS flow is mapped to another data bearer. And what is the significance of the data bearers? As I was mentioning, the data bearers are the logical connection that is established with radio resources. So for each data bearer, we have certain radio resources that can be established and utilized by the base station and by the user equipment using the MAC scheduler as the entity to do these kind of QoS guarantees. Yeah, finally, yes, I have 3 IP sessions mapped to 3 different QoS flows, which are in turn mapped to 2 data bearers, and these data bearers have the radio resources allocated. Same thing is even in the other direction when the user equipment wanted to send in uplink. There also similar kind of animation is shown where there are 3 IP sessions from the user equipment side where it has created 3 different QoS flows, and it has done again mapping of the 2 flows into one bearer and the third flow into another bearer, and it is using its radio resources to send the QoS flows in uplink. I guess this slide is a kind of thing help you to better understand what I'm saying. Try to pay attention to this slide for a minute, and if you have any doubts, I will try to explain. But ideally, I expect one of you to explain based on what I was describing for last half an hour, what is happening in this slide. So just pay attention to this slide for 2 minutes. I will ask one of you start explaining to me and to other students what you understood out of the QoS model that is there in the 5G networks and how the mapping is done at different entities in the network. I hope all of you have seen this one. So who wants to speak? Or who wants to explain what is happening here? So Viren, can you pick some name? If you are still out there.
Yes, sir, I'm here, sir.
Can you read out one name who is in the session and ask them to explain what is happening in this slide?
I think, sir, Anvisha is there, sir. She can explain.
No, I want those who are not speaking regularly to explain, not the one who
Okay.
who never spoken so far. You pick their names.
Shaurya can say something, sir.
Who is that?
Shaurya Gali.
Saurya? Saurya, right?
Yeah, Shaurya, yeah.
Saurya, are you there?
Or sir, Supriya is also there, I think. Can also speak.
Okay. Okay, Supriya, you want to, can you explain?
So I can try, but I don't know how much I can. Okay. Hello.
Yeah, please go ahead, Supriya. Yeah.
Yes, sir. So as you said that we are seeing some different like WhatsApp, Skype, different say.
So are you explaining from left to right or right to left?
So from right to left.
Okay, so okay, start with IP flow. Let's take an IP flow or our IP session, okay?
Yes, sir. So when we try to make a video call in WhatsApp, so the first PDU session is established. So yeah, so the request goes from. I think I should better start from this side because on the user side it will be better.
But I was mentioning that the marking of the QoS flows or tagging with the QoS flow identifier is done by the UPF, right? So you should
Yes,
start only on the right hand side.
yes, sir. But I'm not able to link this last. Like when the first one, in the WhatsApp video call, when the session establishment is done, so one-to-one connection is made between this UPF and the Gnode B. Like the first, the request goes from UPF to like the request first goes like from so it's one-to-one connection is made between UPF the like, single PDU session is established and that using SDAB it goes one data bearer connection it goes to the data bearer and then it goes to the UE. And similarly, for the YouTube stream, also a single QoS flow video session is established, and a single connection is there between the video session, the QoS flow video session, and the data bearer. But we can see that for this, there are two QoS flows mapped with the single data bearer, DRB2. Then these two are for one is for WhatsApp and one is for YouTube. Like these both video sessions are mapped with the same with the same data bearer and in all others there are single one to in the rest one there are single one-to-one connection between the video session and the data bearer. But here for the WhatsApp and YouTube like you said that many to one can be established, so that is being established. So for the rest of the one-to-one is being established and then it moves on to the UE part and
Okay, thank you, Supriya. I think you are more or less accurate. But you have to summarize what she is trying to say. On the right hand side, there are 3 PDU sessions that are established with one user. If you look at the choice of the PDU sessions, the bottom one that you see it here. So do you know why, what is the significance of this particular PDU session? Can somebody comment?
It would be for voice over IP, I guess.
Yes, it is for voice over IP and even other kind of services that operators wants to provide. For example, voice over 5G could be the one service that they can use to launch. They can serve. Voice over 5G is one such service that operator can launch. For that, they have to establish one PDU session from UPF to the user equipment in the case of voice over IP. So that is the meaning of this particular thing. In this case, we are showing not only the voice, we are also showing the video. So what I'm saying is, for voice application and for the video application, we have established one PDU session. And also look at the mapping of, okay, so these are the 2 QoS flows. These are part of one PDU session. Look at how we are mapping these IP flows to the QoS flows. So you can see there's a 1:1 mapping between voice session to the QoS flow 5. Similarly, for video session, we have the QoS flow 6. So is that clear? So we are saying 1:1 mapping between IP sessions to the QoS flows, where we are marking it as having with QoS flow identifier 5. We are marking video as having the QoS flow identifier 6. That is the thing, meaning here. And interestingly, if the operator have tie up with like Netflix or Amazon Prime or some other service or third-party OTT provider, they can create another PDU session and they can map all the packets that belonging to those IP sessions to a separate QoS flow. So that is an example, but it's not that they have to map. They can also be mapped to same QoS flow as well. But very often, the one that they wanted to provide guarantees and they wanted to make revenue, they try to provide exclusive separation by putting separate QoS flow identifiers. That's why you can see voice, video, and Netflix, which are kind of what operator or their associated OTT players wanted to provide. You can see 1:1 mapping. Then we have all the other IP sessions like Best Effort, WhatsApp, Skype video, and YouTube, which are all mapped into the Internet PDU session. And here we have the 4 IP sessions that are out there. Look at the mapping of these 4 sessions into the QoS flows, where you can see the best effort is given to one QoS flow with the identifier 1. This is given to QoS flow 2 with identifier 2, where both WhatsApp and Skype are kind of given the same QoS flow. That means the treatment of the WhatsApp video and Skype video by the cellular network, in this case 5G network, is the same, because we are subjecting it to the same QoS parameters in terms of the loss rate, jitter, latency, and other thing. That is the meaning of this.
Welcome to use cell phone 01.
Okay, so then we have, now look at the mapping from, so this is the step 1 mapping that I was talking about, which is done at the UPF, where we are taking the IP flows or IP sessions and we are adding the QoS flow identifier to create QoS flows. So, and the IP packets with the QoS flow identifier are pushed to the base station. What the base station does, base station is having one SDAP instance running for each of the PDU sessions, because there are 3 PDU sessions for a given user. For the same user, it has 3 instances of SDAP layer is running. So what it is doing, where one for each of the PDU session. So it is taking these 3 QoS flows and mapping them into 2 different data bearers. And for this QoS flow, it is mapped into separate data bearer. For these 2, it is mapped into 2 separate bearers. Even though you see here the names QoS flow identifier 1, 2, 3, 4, 5, 6, it need not be the case. I can also have the QoS flow identifier 1 used in another PDU session as well. Within a PDU session, we cannot reuse the QoS flow identifier. That means all the QoS flows in a given PDU session should have different QoS flow identifiers. But across the sessions, we can have same QoS flow identifier, because the meaning of this QoS flow identifier, I will explain in the following slide. So yeah, that's what you can see. Finally, we have these bearers. So then the packets are going to the user equipment. What user equipment is? It is taking the packets of these bearers and again giving to the respective IP applications. Even in the reverse also, what happens is, if it is a reflective QoS, what you do is you take the packets that is coming in the reverse direction and you assume that they will also have the same QoS flow. If not, we have to use RRC signaling between GNodeB and UV to create a similar kind of QoS flows. That's what I was showing it here. Then we can do the marking, where your user equipment does the marking by adding the QoS flow identifier, then it will go in uplink. So any comments or any queries anyone having on this?
So the best effort services, meaning that the internet service provider doesn't provide any guarantee of the quality and delivery, right? So why is there any significance of providing a single QoS flow for that?
Oh, no. Okay, that is important, interesting, Madhuri. Even though we are using the word best effort is all the traffic for which operator doesn't want it to give any QoS guarantees. That is the meaning of best effort. Okay. And when you say that we are giving, in this case, for the best effort traffic QoS identifier, flow identifier 1, basically what it means is that it is subject to certain kind of QoS guarantees. But as the name says, best effort should not be provided any kind of QoS guarantees. The QoS flow 1 with identifier 1 doesn't really give any guarantees. but still we mark it as QoS flow identifier 1, where inside we say that, okay, you send at your best, but don't worry about giving reliability or latency guarantees.
Okay, sir. I was like more concerned about why it is single mapping.
No,
Why
again, it is a toy example. What I'm showing is a toy example.
Yes, sir.
And see, the 3GPP doesn't really talk about how you should be mapping IP sessions to the QoS flows and how you should multiplex or map the QoS flows to the data bearers. It is up to the operators, depending on the way they wanted to differentiate the traffic or they wanted to get the revenue and get the service differentiation. It is all up to the operators to decide. It is just a toy example to show that how a user equipment can be part of 3 PDU sessions where we can do the multiplexing of the sessions to the QoS flows in turn to the data bearers. Okay. So any other comments or any other queries? Is that clear to all of you? Oh.
Yes, sir.
Okay, so for each QoS flow, we have something called QoS profile. Again, I don't want to go deep into these things, but at the high level, what the profile says is that how a QoS flow should be treated. For each QoS flow, we can have something called QoS identifier, and we have something called allocation and retention priority. There are different priority levels, all the way from 1 to 15, where 1 is the highest priority. And we have something called a preemption capability and a preemption vulnerability. What this basically means is that when you have different QoS flows for the same user, when you are having a problem of limited number of radio resources, or when there is a congestion in the network, you wanted to give more priority to those QoS flows which require higher QoS guarantees. That can be ensured by using the priority level. By marking some flows with the priority level 1, we can try to allocate the available radio resource to them, and all other flows we can discard or we can put it in the buffer. And also what the preemption basically talks about is that whether the radio resources that are allocated to a given QoS flow can be taken away by the base station to allocate to other QoS flows. So that is the meaning of that. Okay. And also we have something called guaranteed flow bit rate and maximum flow bit rate. This kind of says that what is the minimum that your QoS flow should be provided in both the downlink and uplink, and in the extreme case, how much it may demand. So this is the minimum and this is the kind of the maximum, so that we can able to see whether these flows are getting or not. Also we have loss rate as well. And also we have delay critical resource type or not. We can flag whether this application or this flow is belonging to any mission critical application. If so, that can be given separate kind of priority by the scheduling algorithms. We also have something called notification control. This basically means that when there is a congestion, and if you are, let's say, the base station is dropping the packets for a given QoS flow, notification control says that whether the base station should inform to the UPF about its dropping certain number of packets because of its inability to send them. So where SMF can configure the notification control and accordingly can get to know in the extreme situations. And in that case, what the UPF can do is it can start modifying the QoS flows, or it can try to release some of the QoS flows and do other kind of things. These are the further case of QoS flows. And if it is a non-guaranteed bit rate, we only do the reflective QoS and with the certain other parameters. We don't really worry too much about non-guaranteed QoS flows. And we have something called flow related characteristics. So these kind of describe how a flow should be treated as it is traversing between the user equipment and UPF. As it traverses, how a given QoS flow should be treated by various entities. Like in this case, we have the UPF, we have the base station and the user equipment, how they should treat. So we have various parameters. Based on that, the different entities try to differentiate different flows. One of them is the what kind of flow it is, GBR, mission critical, or non-GBR. What kind of priority level? I was mentioning about 1 to 15 priorities where one is the highest. Delay, packet delay budget. What is the acceptable delay between the user equipment and UPF? So we can say if it is voice, around 30 millisecond. If it is like a video conferencing, 200 millisecond. This is the acceptable delay between these two when the packets are traversing in the cellular networks. And what is the acceptable error rate that you should be guaranteeing between the user equipment and the base station? So this is done between the user equipment and the base station at the RLC layer and the PDCP layer. And all these things are measured at a certain time scale. The averaging window is the time scale at which you wanted to guarantee and the error rates and the delay budget and the guaranteed bit rate and the maximum bit rate. And certain applications like mission critical applications, they demand the maximum data. They kind of require sending certain amount of the data in a burst. They specify that how much data will come in a burst by the handset or by other remote entity, which should be sent in a burst by the radio network. This is called something called maximum data burst volume. Okay, so these are kind of guidelines that are kind of provided to the various entities. All the entities like PDCP, RLC, MAC, at both the user equipment and the base station has to be appropriately configured based on how these characteristics are varying for different QoS flows. So we have the mapping of the QoS identifier to the QoS characteristic defined in this table in 23.501. Maybe I'll show you this and stop today's class so that you can appreciate what I'm talking about here. So this is the description about HDAP layer, which today I described. Yeah. So whatever I was presenting today is defined in the 37.324 document. Okay. And if you come back here, yes. So look at here. This is the 5G QoS identifier value. And this is the resource type, GBR, mission critical or non-GBR. The priority level that you wanted to give, and the packet delay budget between the user equipment and the UPF. Then the packet error rate between user equipment and the base station. And like mission critical applications have default maximum data burst volume, which is not defined in the case of GBR and non-GBR traffic. And all these parameters should be checked over the time window. In this case, it is defined as 2 seconds. Every 2 seconds, you have to kind of guarantee that the packet error rate, if it is conversational video, should not exceed 10 to the power of -2. Similarly, for conversational video, the latency between your handset and the UPF should not exceed 100 milliseconds. That you should ensure when you are measuring every 200 milliseconds. So that is the meaning of this. You can see, interestingly, there are many different 5QA values that are defined, 1, 2, 3, 4. And I think I highlighted one thing that is related to the intelligent, like vehicle to vehicular communication kind of networks, where you can see it is having 5 QI value of 84, where we are talking about the packet delay budget is 30 milliseconds between UPF and the user equipment. Of course, even though I'm talking about V2X also has something called V2N mode, where vehicles also can talk with the base station. In that case, you can think about it. But if it is like a vehicle to vehicle communication, then also you can say that these two vehicles should exchange the data between themselves over a time window of 30 milliseconds, where the loss rate should be 10 to the power of -5. And it has the maximum burst value of 1354 bytes. That means you can expect that these applications generate data where each data is having size around 1300 bytes. you should be able to provide data bearers which kind of able to pump this amount of the data over the wireless link. That is the meaning of this. So we can see V2X messaging for the collision avoidance, platooning with high, I think location area code, I guess, this one. So visual content. So you can see 63,000 bytes also is expected in one of the use case. Visual content for cloud edge split rendering. So there are some nodes that have been defined. You can see that unlike in internet and even for that matter, even in Wi-Fi networks, you don't have this kind of guaranteed queues defined when you're setting up the calls or establishing the IP sessions. Where we have something called admission control running at the base station, it can try to decide whether to admit new flows, QoS flows or not, depending on the availability of the channel resources. If not, it will inform the UPF. Then UPF has to figure it out whether to wait for some more time or do something else. I wanted to just go through this document to look at what I meant. These are the standardized 5QI to QoS characteristic mapping. So basically what it means is that when you are establishing a new QoS flow and I was mentioning, right, if you recall,
Sir,
this is nothing but 5QI as long as the value of 5QI is less than or equal to 64. So try to understand what I'm trying to say that. So ignore this part. At the high level, you can assume that the QFI, the QoS flow identifier that we are kind of assigning when you are getting the IP packets from internet, that is nothing but 5QA. That means what your UPF does is it looks at each IP session or the IP packet that are coming, it will assign one of the QFI. Let's assume that for this it has assigned it as F equal to 5. Or this one it has assigned as 10. So if I have assigned it as QFI equal to 5 or 5QI equal to 5, then what you have to do is you have to go back and look at this document. Okay, unfortunately, looks like 5 is not defined. Okay, it is there, yeah. Oh, okay, look at here, 5. So it is actually defined for voice over IP related signaling messages, but where it is talking about having the delay budget of 100 millisecond and the packet loss rate of 10 to the power of minus 6. Now, you are asking something, Madhuri?
sir, in slides it is like the priority is from 1 to 15. How, like, is it like relative priority? The document that shows it is having.
No. Okay, those are relative priorities. So we have two things. We have QFI and also have the priority values. Both are different. Okay, maybe I will explain that here. Can you see this slide? Okay. Look at these two. The QFI is nothing but what you see in the column number 1. As long as the value is less than or equal to 64, because QFI is only 6-bit. We have some other mapping if it is more than 64, because you can see we have even values greater than 64 defined as 5QI. Okay, and the priority is the one, this one. So the priority comes into the picture when there is a challenge in providing QoS for all the QoS flows of a given user. So then the relative priorities are used to prioritize some of them one over other one.
There is one slide you showed, sir, just previous some slide where you mentioned priority from 1 to 15. 1 is highest. What?
Oh, okay. You were talking about, I think, where is it? Okay.
Yeah.
So this is okay. This is some other priority actually. Yeah. So this is something else. That this is, I guess, this is done by at the base station level. when base station is scheduling the user traffic, when it has challenges, it uses this one. But I think this is the one that is coming from the UPF side. So look at here, this is the one that is assigned by the UPF. When the IP sessions are coming, UPF is the one that is assigning to each IP session one of the 5 QA values. Let's say it has assigned 5 QA value as 1. That means all the entities, that means the base station and user equipment, will come to know that these are the default values for this particular IP session. But then what happens? I think that's what you are trying to ask here. We have, okay, maybe let me check why I'm saying it is 1 to 15. Let me check one more time whether it is 1 to 15 or they have further extended. Yeah, okay. So let me check one more time. Yeah, what you're saying is here the numbers are even going up to 80, 90 also, right?
Yes, sir.
Okay. I have to check that. So these are kind of treat like these are like a relative priorities, and this is the absolute priority. Okay. Okay, so any other comments? I think already we are running late. So Viren, I think you have to take attendance one more time now. Because many students left without even telling me.
Yes, sir.